everyone. So I'm Manon Rumeau. I'm on my final year of PhD at the University of Birmingham in BIFoR. And today I'm going to try to convince you of how fascinating the nitrogen cycle is. So my PhD is on nitrogen cycle in two Fourier carbon dioxide enrichment, BIFoR phase and nuke phase. So during my PhD, I had the chance to go to those two existing phase experiments that are quite unique because they are set up in mature forest. So I realize actually now that I'm the first one presenting phase experiment, but so those two phase experiments have a very similar experimental design. They both have 3 rings that are fumigated with ambient air, which we call the control, so CO2, and 3 rings that are fumigated with a concentration of CO2 of 150 ppm above the ambient concentration, that we call CO2. And this fumigation happened from the bottom to the top of the tree, thanks to this pipe that are transporting the CO2 to the top of the canopy. So why studying nitrogen cycling under elevated CO2? It's because we know that rising atmospheric carbon dioxide is projected to boost terrestrial plant production through the so-called CO2 fertilization effect. But we also know that when nitrogen availability is considered in the models, carbon storage production can be reduced between 25 to 74%. There is a big uncertainty here, and this uncertainty may be even bigger actually in mature forest because there's been really little experimental data from mature forest, even though they are more nutrient limited, but they also have developed complex interaction with mycorrhizal fungi, with rhizospheric bacteria, which could help alleviate this nutrient limitation. So basically, we don't really know. But according to models, to meta-analysis, what we know is that biomass response to elevated CO2 is dependent. One of the drivers is the soil-CN ratio, so basically the nitrogen availability. And while nuke phase with a soil-CN ratio of 13, it's not so much nitrogen limited. BIFoR phase with a soil-CN ratio of 18, we expect it to be quite nitrogen limited and kind of sit at a tipping point where the nitrogen limitation could limit the biomass response to elevated CO2. So the purpose of my PhD is really to understand if nitrogen will limit constrained tree growth under elevated CO2. And as I'm a soil scientist, I want to answer that looking at the soil nitrogen processes. So I'm looking at all these different processes in the soil, and my main hypothesis is that under elevated CO2, we'll see an increase in carbon allocation below ground that will upregulate nitrogen fixation, so more new N coming in, basically, and also upregulate nitrogen mineralization from the soil organic matter. But we also hypothesize that this higher microbial activity in the soil resulting will stimulate nitrogen losses from nitrification and denitrification, which could lead on the long term to progressive nitrogen limitation. So basically, I'm looking at that using a stable isotope, 15N, to trace and measure all these different rates, all these different processes, so nitrogen transformation in soil, but also soil-atmosphere exchange, so looking at nitrogen fixation and N2 emissions. So if we move on a bit on the result, at least already just on the basic soil properties at BIFoR phase that we measure for a year in 2022. As we hypothesized, we do find higher carbon, dissolved organic carbon, under elevated CO2. We also find a higher ammonium availability with some seasonal effect. But on the contrary, we do not see any effect on nitrate availability. It's even usually lower. And soil moisture was overall downregulated under elevated CO2, and especially in the dry season, so in summer of that year. We also measured during that time the net mineralization, so how much nitrogen is mineralized. And we have strong evidence that natural mineralization is upregulated under elevated CO2, and it delivers an additional 26 kilograms of nitrogen per hectare per year under elevated CO2. And we could see quite strong correlation with the soil dissolved organic carbon, which supports our original hypothesis that higher carbon allocation below ground and hence stimulate nitrogen mineralization. Then we used isotopes to really partition between how much ammonium was being produced, how much nitrate was being produced, and also how much microbes will immobilize these two nutrients. And we did that in this intact soil core, where we could preserve the influence of roots, which is really important here, and also preserve the influence of the soil structure. And we did find evidence of higher gross ammonification, so more ammonium being produced, which is a sort of the favorite form of nitrogen for the trees. And this higher production of ammonium was also correlated with higher soil respiration and the higher fine root biomass. But conversely, nitrification, so the production of nitrate, was downregulated, and this was negatively correlated with the root biomass. So the higher root biomass and the elevated CO2 led to less nitrate in the soil, which is quite important when we look at nitrogen losses, because more nitrate will lead eventually to more nitrogen losses, either by leaching or in the atmosphere through nitrous oxide. So we also measured nitrogen fixation, but we didn't see any effect of elevated CO2 as well as nitrous oxide and conversion in N2. So we pulled all these different nitrogen rates together under elevated CO2 and eCO2. And we compared them with also the nitrogen being taken up by the trees, which is estimated by people looking at the above ground, so Carolina here. And what we could see is that actually the nitrogen mineralization matched pretty well the nitrogen uptake by the trees. So basically that means that the higher nitrogen demand under elevated CO2 that we see here is 10 kilogram of nitrogen approximately is being sustained by the higher nitrogen mineralization. And all of that seems to be correlated with more carbon in the ground. But from that, what we really wanted to understand was really what was happening between this higher fine root biomass, higher carbon below ground, and this different effect on the nitrogen dynamics. And one hypothesis that we had was that change in the soil exudate-CN ratio, because we did find higher, the exudate-CN ratio increased under elevated CO2. So we wondered how that will affect nitrogen dynamics. So to isolate just this effect, a change in soil exudate-CN ratio, we designed another experiment that we call the automated root exudate experiment, and we replicated this artificial exudate cocktail with different exudate-CN ratio. So we used 11 different compounds, so quite a complex system to what is usually done, that had two different CN ratio, two treatments, one that had a CN ratio of 4.4 and one of 7.4. And we had this continuous addition of this exudation cocktail during 6 months. We also wanted to look really what was the effect on of roots, fungi, and bacteria on these different nitrogen dynamics. So we use this exclusion bag that could exclude roots or exclude roots and fungi. And after 6 months, we measured nitrogen mineralization in the soil. The first thing that we saw that was when roots were present, so in the horizon here, we will have an enhanced ammonification, so more ammonium being produced, and an inhibition of nitrification, which support our early, what we've seen in this in situ core, where the higher fine root biomass and the elevated CO2 stimulated ammonification, but downregulated nitrification. Second thing that we saw was the high exudate-CN ratio was stimulated gross ammonification. So here, if you look at the purple, this is especially evident in the horizon. So increasing the CN ratio of the soil exudate does stimulate nitrogen mining. And it was also stimulated the fungal nitrification in the 41 micron bag. And what was quite interesting is that in the low CN ratio, so we were still adding quite a lot of carbon, well, compared to the control, we were not adding anything. We had a lower nutrient immobilization, also lower nutrient mining overall, which led us to think that in that treatment, the microbe preferred to basically utilize these exudates, so the amino acid that we were adding, instead of mining for more nitrogen. So it led us to understand that actually increasing the soil exudate-CN ratio changed the microbial nutrients acquisition strategy to a more nitrogen mining strategy. So it's basically if we had carbon and nitrogen, they're going to they're not going to change their nutrient acquisition strategy. What if you add more carbon compared to the nitrogen? They will use this extra carbon to mine for more nitrogen. And this is especially important when roots are present. So altogether, this helped us to kind of understand the mechanistic behind what was happening under elevated CO2, that the higher fine root biomass under elevated CO2 will stimulate ammonification and inhibit nitrification. This inhibition of nitrification is probably through two ways, because more root biomass, more root exploration will reduce basically the hotspot for nitrification, but also we wonder if maybe trees may not be exudating more biological nitrification inhibitors, or just by having more roots spreading these biological nitrification inhibitors. And secondly, so by increasing the exudation ratio, they favor this microbial nitrogen mining strategy, which stimulate mineralization. So this is what really is happening in BIFoR. We have upregulation of the nitrogen mining, but also a conservation of nitrogen, which could really help seems to really help sustaining the higher nitrogen demand. And I just wanted to show a few things about adduct phase. So I also looked at the various things at adduct phase, and things are really different. First of all, we do not see any upregulation of nitrogen cycling over there. This can be due because we also don't see any evidence of more carbon being allocated below ground. So the fine root biomass is actually lower from our data. We don't see any effect on the soil dissolving carbon. But we do see higher nitrate concentration and slightly higher phosphorus concentration. So there's probably more, because phosphorus is limited in this ecosystem rather than nitrogen, there's probably more investment in phosphorus acquisition rather than nitrogen acquisition. But this actually would have a talk, much more details on that by Mikael tomorrow. So on the whole, what's happening in nuke phase, he is much more an expert than I am. So this really highlights that we have very divergent response of forests to elevated CO2 between BIFoR phase and nuke phase. At BIFoR phase, we see that elevated CO2 increase root production, increase exudation, and impact rhizosphere nutrient dynamic to supply more nitrogen to trees. How long can this be sustained is still unsure. And also, how does it affect the soil carbon is unsure as well, because if we stimulate mineralization, we also stimulate carbon losses from the soil. While at adduct phase, we see that the plant response is well limited by phosphorus availability, but the plant influence on phosphorus availability may be actually insufficient to elevate this P limitation. So these two divergent response of these two temperate forests really highlight that understanding the underlying mechanism of how forests react to elevated CO2 really matters if we want to scale up and improve those models. Otherwise, we need to have a phase experiment in all the diversity of forests existing. And again, about this conference that is about communities, we know that improving this model is really important, and it's really important to reach policymakers about it, but it's also important to reach the next generation. And I just wanted to highlight that in BIFoR, actually what is really, really unique is also its involvement in science communication, in science outreach, in citizen engagement. And there is Dr. Samantha Dobie and Jeremy Pritchard who lead a lot of this aspect, and they have a whole website. It's called BIFoR in a Box, where they create a lot of materials, but they also make us involved, just as PhD, into this. So yeah, I just wanted to highlight that it was really important to engage in the science communication. So I just did a small part of it, of writing a communication paper and doing some lecture, but this is really important, and actually people are really interested in our research. Thank you very much. That's all for me.